I'm the lab technician for Rapid Tech. That means I'm the low man on the totem pole. They break it and I try to fix it. So we're going to take a whirlwind tour of 3D rapid prototyping starting in here. We have several different types of machines in here. Everybody familiar a little bit with 3D printing? The basic concept is we take a 3D model and then the software slices it. How big the layer is depends on the software in the particular machine. And so after we've sliced it, then we send it to the printer, and the printer basically prints the bottom layer, then the next layer, then the next layer, and keeps going until it's completely printed the entire model. So all the machines pretty much work that way except for the stepchild in the corner that prints it upside down. It starts at the top and works down. So the big machine and these two little machines are what we call stereolithography, SLA. They use what's known as a photopolymer, which is kind of a funny name for a very thick plastic goop. And what happens is, get in there, we have a UV laser that's attuned to the right wavelength, and where it scans across the surface of that liquid, wherever the UV laser hits, it does a phase change and creates a plastic. And then again, we build a layer, we dip down just a little bit, bring some more liquid plastic across, and then we do the next layer. And this builds some rather durable parts, although they have one little shortcoming. They start off clear and over time turn yellow. But they make great prototypes. This is a prototype of a heart that we did for a medical concern. They basically had a new catheter. So they plumbed up our heart after we built it, and now they teach doctors to drive catheters through it. I'd much rather they did it on this than someone like me. So this works out pretty good. And each of the machines have a different type of photopolymer. There's quite a range of different material capabilities you can put into the machine. They're not cheap. 1 liter of that photopolymer is $610. So it doesn't come quickly. Somebody came in here and wanted a 10-centimeter box. Well, first of all, it's that big, not that big. And the price was about $3,000. And we explained to them they could go to Radio Shack and get a plastic box much cheaper. So rapid prototyping isn't always the correct answer. In addition to the SLA machines, we have 2 very old thermojets. These print entirely in wax. Where this comes in handy is we can print a wax master, and then they can use that for sand casting or whatever, to where this is very big in the casting industry. And the beauty of it is it actually has 16 micron details. As you can see, we made a mold from it, but you can pass that around. Please don't drop it. Wax is very fragile. But the idea is this machine is used extensively for making master castings. We have a laser engraver, which is kind of an auxiliary piece of equipment that's used to make mold boxes and other things like little UCI logos and things like that. But we've had students in engineering build entire buildings by cutting the balsa on the laser engraver, simply because it cuts straight lines, unlike students. And it does a repeated time after time, so the end result is we get a lot better quality. And they actually built a skyscraper about this high for their tilt table so they could test it. Worked out pretty good. In this corner, we have the weird one. This is an Envision Tech. It uses, everybody know what a DLP projector is? Digital light projector? It's basically a little chip with a whole bunch of mirrors, tiny little microscopic mirrors. And then it projects the entire image, just like a projector on a screen. And wherever the image is projected, it cures the resin and makes a part. And this one kind of starts, the platform will come all the way down into the resin, and then it slowly comes up. So it's upside down. All the others, the part goes down. This one, the part comes up, just to be different. To give you an idea that we can use different materials together, this is a model of a medieval torture device called the Pear of Anguish. It's obvious it goes into various holes throughout the anatomy, and then once they put it in there, they would just basically turn the screw and keep turning the screw until you gave in. But this uses a water clear SLA from the Sony. It uses the handles made on the Envision Tech, and there's some other parts built on another machine that we no longer have. So the idea is you can use different parts for different requirements. If you need a flexible part here and you need a hard part there, the different machines give you the ability to make the different parts and put them together to make what you really need. And there's actually some machines, unfortunately we don't have one, that can print in what we call digital materials, to where they put 2 cartridges in the machine. One can have a very hard, dark material. The other can be a very flexible material, or maybe a light material. And then it can mix them on the fly. So you can literally build parts that have a hard shell ring with a flexible rubber middle, all as one piece. So that's this room, which is the SLA, the Envision Tech, and the Thermojet. The next doors down, we have another technology which uses a powder. In here we have 2 machines that are called selective laser sintering machines. These can work with a wide variety of materials. Everything's from plastics, carbon filled, nylon filled, aluminum filled. There are versions of these machines that work in metal, and they can print Inconel, stainless steel, cobalt chrome, titanium. The advantage of using metals in these type of machines is there's very little or no waste. Because the way the machine works, you have 2 bins, one on either side, that are filled with the material you want to use. In the middle is the build area. And it will basically inert the chamber. In our case, we use a whole compressor and a special filter system to make 99.9% pure nitrogen, which we then inert the chamber with nitrogen. We then heat the bed up to about 183 degrees centigrade. Pretty warm. When the powder comes across, it makes a nice 4/1000 of an inch layer. Very smooth, very packed. And then a CO2 laser scans where it wants the part to be. And wherever the laser hits, it takes and adds just enough energy to take the powder above the glass transition to where you actually get a liquid or a goo. But it makes a part. It basically fuses it into a part. And again, layer by layer. So we build up the parts 4/1000 of an inch at a time. These parts aren't pretty because they have a rather grainy structure, but they are extremely durable. In fact, this technology in its various forms is used predominantly in industry above all the others. Boeing makes all the air ducts for their commercial airliners and their fighter jets. It used to be they would have to make them in 3 or 4 pieces and ultrasonically weld them together, and it took a lot of work. Now they print them as one piece, take it out, shake it off, and it's ready to go on the airplane. So it saves time, energy, money. And you can do quite fine detail. This was all printed as one piece, and somebody's managed to break it. Maybe I can get it together. Maybe not. Oh well, I'll have to get another one. But this was all printed, hinges and all, as one piece. So you can see there's a lot of capability, and it can get pretty fine detail. Not as fine as some of the other machines, but by the same token, it's a lot more durable than the other machines. And you can get pretty fine detail. And the metals machine, somebody stole all my metal parts. I don't have any. But there are the ways on this machine you can do things that have living hinges. If I can get it apart, which I can't. There we go. So you can do living hinges, you can do metal parts. And like I say, there's a wide variety of materials that you can use for this machine, and they can custom blend them on the fly. So if you need a specific capability, you can actually get it right from the manufacturer, and then it's just filling the machine and running it. These machines, if you wanted to build a tiny part, okay, if you want to build a tiny part, it's not quick. It's not what you would call rapid. Okay, it's certainly not the replicator from Star Trek. Okay, to heat the machine up to where it's ready to build can take about 2.5 hours or more. And however long it takes to build the part, which can be 10 minutes, 100 minutes, 6 hours, depending on the complexity. And these can hold parts about 14 inches deep and 10-inch diameter. If it'll fit in there, they can make it. The problem is that you've heated all that powder up to 180 some degrees centigrade. So now you have to cool it all the way back down before you can open the chamber. The nylon 11 that we use, if you open the chamber with the temperature above 50 C, it changes all the properties of the nylon. So it's 6 to 7 hours after you've built the part before you cool it down enough that you can literally take the part out. And when you go to take the part out, you basically get, well, this is a bad example, but as best I can do, you get a big round cake, and then you have to take it in another room, and it's like an archaeological dig where you dig the part out of all the powder that's holding it. But all the powder that you take out that you didn't actually use can go back in the machine, so it's completely recyclable. And the powder we use is called Riceland, which is a nylon 11 FAA certified. It's also a green product in that they actually make the nylon from the shells of the castor beans. So it's a renewable resource, green product, which is nice to have. It's not cheap, but it's nice. So any questions about how SLS works? I'll give you a good example of where you wouldn't think it is. Up in Irvine is a company called Glidewell Dental. When you do your bite marks at the dentist office, they are sent to Glidewell Dental. They laser scan the bite marks into the computer. They then use that and send it to a metals machine, which actually prints your teeth in metal, which they then enamel over to get the finished product, and there you have your teeth. It's all digital from the time it comes in the door to the time it goes out. And they're actually printing your teeth on metal. Some of the other machines print hearing aid shells. And they'll have a huge bed and they can print hundreds of hearing aid shells at one time. It works out pretty good. And now we'll go down to the cheap end of the sense. This is low end. I'll move to the back so everybody else can get in. Come on in. It won't bite much. These are the low-end printers, kind of like what you would call the home hobbyist printer, but they work on the same principle as a lot of the bigger printers that are used in industry. It's a process called FDM, or fused deposition modeling. And basically what it amounts to is you take an ABS wire, or we can use PLA, which is cheaper, but an ABS wire, and you heat it, in this case to about 240 degrees centigrade. You then push it through a very fine nozzle, and wherever you want the part to be, you extrude it onto the platform. It's kind of like a glue gun on steroids. It's a glue gun with its own XYZ table, basically. So we build, again, all the parts are built layer by layer by layer. And FDM is pretty durable. ABS plastic is used a lot in industry for form, fit, and function testing. They've done printed an entire intake manifold for an engine in FDM, turn around, bolt it on an engine, and test it to see if it worked the way they thought it would. Things like this. So it's a very functional piece of 3D prototyping equipment. These, however, are more the hobbyist level. And this, by the way, is the 3D printing lab for students. You can work to come in here, charges $4 an hour for however many hours it takes to build your parts, and you can actually get parts built in here. These machines, we use what's called a raft, which is basically a throwaway part that interfaces between the actual metal surface and the part we want. And then we print on top of it to get the individual pieces that we need. And then of course you have to peel the raft off of the part to get to the part. But it makes quite a variety of parts, and these are all wood clamps, although for some reason somebody seems to have a thing for minions, so they were printing their own half minions. So some of them are happy, some of them don't look too good, but we'll see how it goes. So fused deposition modeling is one of the big ones. There are machines like the Fortis 900. The print bed on it is about 3 feet by 3 feet, and you can go up quite high, so you can literally print giant objects in ABS plastic. And they have the capability of using other things like PEEK, where you need fire resistance, stuff like that. They have quite a variety of materials, and the industry is spending all its time now making more materials. That's the big thing. They've got the ways to build things, now they're just expanding the materials they have available to get different capabilities. And it's going to continue that way. Any questions? I only have one more area, and that's down in the CNC lab. Well, I do have another area. We'll go down here. This is the powder-based room, so powder gets into everything. This is kind of like the low end of 3D printing as far as what we have for technology, but this machine actually has the advantage of being one of the few in the world that actually prints in color. It can actually print in 16 million different colors. As you can see, it has quite a range of colors. And the way it does that is it basically has a binder and 3 colors, cyan, magenta, and yellow, and 4 print heads. And the print heads are actually HP number 11 inkjet print heads. You purge all the ink out and put your binder in them, and then you use it. And the way it works, we have a vat of powder, and this is a kind of a plastic plaster composite, very finely ground powder. Okay? And the feed bin comes up and sprays 4 thousandths of an inch of powder across in a nice even flat layer. And then the print heads, which are inside here, basically come across, and they go row by row back and forth, and they deposit binder in whatever color is necessary to make the model. Now the color doesn't go all the way through the model, it's only about 1/8 of an inch in. The middle of the model is white because you don't need color where you can't see it. But the color is physically in the part, it's not just kind of like painted on, it's actually in it. So that gives you the capability to do a lot of things you can't do with other types of 3D rapid prototyping. We have made geo models where you have the whole landscape with the hills, the valleys, and all the different colors. One of the things that they've done with it is they've taken turbine blades and they've mapped all the heat temperatures onto it. So you could take a look at the turbine blade and you could see where the red was and know that's not good just by looking at it. Instead of trying to explain it to somebody, you just give them a picture and it works really well. I don't have one here, but there was a company down in Fallbrook that makes automatic transmissions for bicycles, and they couldn't sell them because their salesman couldn't explain to the customer how they worked. So they came to us and we made life-size models in color, but we cut a big wedge out of it to where you could see the insides, also in color, to where they could then show the customer and explain how the insides work and everything. And they started selling them like hotcakes. And they've got a good business going because now they can explain to the customer how it works. And these are more concept modeling, although years ago there was this company, you might know them, they're called Nintendo. They were coming out with the Nintendo Wii, and they had us block prototype their controllers. Well, this one wasn't bad, but the main controller was about that long, that wide, and about that thick. And it cost them $100 or so for the actual part. But when they got it, they suddenly realized that the controller was too big for the hands of their target market, which was 13-year-olds. And they had to go back and completely redesign the controller in order to be able to make it the right size for their target market. But think how much money they saved by not going into production on the wrong part and then having to come back redesign it after they made all the tooling and everything else. So by having concept models, they were able to refine the idea before they got to the point where they were in production. They make the mistakes cheaply, basically. They save time and they save money. So it worked out pretty good for them. Any questions?
Are those two houses from the solar decathlon?
Pardon?
The two 3D printed houses, are those from the solar decathlon?
I can't understand. I hear you.
Those two 3D printed like structures, are those from the solar decathlon? They look really familiar. Like the two houses?
Oh, the houses were an architectural design. I don't know where we got that, but we did it for a customer. Same with that one there. We've actually printed parts on the SLA machine for the University of Vienna that were shown in the Getty Museum as architectural concepts. Some of them I wouldn't want to live in, but they were, you know, exploring the organic architecture, things like this, so we printed models for them. And this works pretty good because this was printed as one piece. You just knock all the powder off. And again, with this machine, any powder you don't use can be recycled back into the machine and used again. So there's very little waste, if any. Now the trick with this machine is when the parts come out of the machine, they're what we call greenware. Even when they're finished, they're fragile, but they're especially fragile when they come out of the machine. So we have to take them over into the little chamber next door there, and basically we use an air compressor and low pressure to blow off all the dust and dirt that's on it to where it's a perfectly clean part with no hangers on. And then we have to infuse it. Now we can either use things like melted wax or wood hardener you can get from like Home Depot or Lowe's. But the best thing we found to use is super glue. You basically take the part and you can either dip it in super glue or you can use a pipette and work it. You get a more consistent finish with dipping it than you do with a pipette. But you basically dip it in super glue, and what happens is there's a lot of air in these parts when they first come out of the machine. It's kind of a loose formation of particles with a lot of air spaces. And the super glue just sucks in like a sponge to all those spaces and hardens, which hardens the part and makes it durable. Well, more durable is a better word. But this one, we did a project for the medical people here. We basically printed a esophagus for a baby. And then we turned around, took this, and used it as the master for a mold that we made. That once we took this out and had the mold was just like the esophagus of the baby, and the doctors could use it. To, you know, for practice, obviously. You don't practice on babies too much. But we had one student that everybody knows that famous World of Warcraft. Well, he made the mistake of his life. He figured out how to pull people's avatars out of World of Warcraft and print them as a 3D model. Problem was he went up to Blizzard Games and said, look what I can do. And they stole his idea because he didn't protect himself. And now there is a company that's associated with Blizzard Games that the whole line of business is building people's avatars in nice little glass cases, you know, with their name on it. And they're nothing more than printing them on these type machines. And because he didn't bother to protect himself, he lost his intellectual property. Something to remember. Protect yourself. Any questions? I'm running out of ideas to what to do. I got one more room, but they're in that other room right now, so we'll be a minute or two. We have any Borderlands players in here? Nobody knows how to play Borderlands. Okay. One of the other things that we can do, the little machine behind you there is kind of like this one, but it's monochrome. But it has one advantage. I can put a powder in there that's like casting sand. So basically I can make masters. This one's already been broken. You can make masters for casting. So you can make a master. You heat it in an oven to 400 degrees for an hour to burn off any volatiles, and then you can literally pour into it and make a one-time mold. You of course have to break it to get it out. This was a first effort at a putter with all the sprues and all the other things on there that have to be ground off. But you can make casting masters by using that machine. Again, one of the advantages of 3D printing is you're building everything up layer by layer by layer, so you can build structures that you can't make any other way. That's the big advantage. If you can think it, you can print it. It may not be pretty, but you can print it. So, any questions?
When all these parts are printed, do they act like ceramic or like they're brittle to fracture?
Well, these being powder-based are softer. The SLA parts, the SLS parts are durable for a long time. I mean, they're using them as ducts on airplanes. That's not something you expect to break down shortly. So, but the SLA parts are durable. They just change color because they continue to cure. But they're still durable plastic. And they have quite a range of plastics to be used in both machines. So, these, like I say, are more for concept modeling. Get your idea across, get it to a focus group so they can laugh at you and say, change this, change that, and then get your project where you want it to be before you design the final version. Makes a big difference. It makes it cheaper. It's also quicker. Well, let's try to get through the other mob. This is not my skull, by the way. I have my spine over there. Yeah, parts of my spine are over there. They did a CAT scan. We converted it to a 3D model and printed it 1/4 scale. You can do medical modeling. That's a big field. Along with 3D modeling, sometimes you have one of something and you want to make more, but you don't have a CAD model. So what you need is a laser scanner that will allow you to scan the original into a computer as a point cloud. You can then manipulate it, fix it, do whatever you want to, and then send it to a 3D printer to print. I don't have access to it anymore because they took it back, but years ago there was a gentleman that owns Evergreen Aviation up in Oregon where the Spruce Goose is, and his goal in life was to have his very own Japanese Zero, a real one that flew. Well, they found parts of one in the ocean. But the Japanese Zero was extensively made with magnesium, and salt water and magnesium don't get along well. So the tail strut was half corroded away. And what they basically did was they brought the tail strut in its damaged state, we laser scanned it, and then in the computer fixed it. Took out, put back the parts that were missing, put everything back the way it should be, and then we printed masters for casting. So where they could then take the masters up and print a new part to go on the Japanese Zero. So that gives you an idea. Laser scanning works hand in hand with 3D printing. Because a lot of times you only have an original. You don't have the ability to just start from scratch. One of these are old radios from the 40s. But where's the other? Yeah, here it is. The grills that go in these things warp and break over time. Well, the guys restoring these radios have no source for these. What we've done for them is laser scanned the grills into the computer and then fixed it all up, made it pretty, and printed them. So where they can now have grills to go in. I don't think this one fits too well. Yeah, it does. If I put it in right, maybe. But the idea, oh, he's got gunk all over it, that's why it won't go in. But the idea is we can make new replacement grills for parts that you couldn't get any other way. In the casting room in there where their other guys are at right now is one of the projects is we have some grates for a cast iron stove that's in a museum. Well, the grates are pretty much shot, and we're basically making molds to build new cast iron grills to go in there to replace the ones that are missing or damaged. So 3D printing and 3D scanning go hand in hand. And this is kind of the low-end 3D scanner. It works either with or without a little table platform that rotates. And basically, one scan isn't enough because basically the laser goes out, bounces off, and comes back. So basically, you take a scan, you turn so many degrees, you take another scan, and after you've done 360, you have to take all those scans and stitch them together. And when you're done, you have a 3D point cloud of the model, which you can then use in the computer to make your part. In the back room back here, we have one other technology. I don't know how we're all going to get in here, but let's see. This is a polyjet machine. It's similar to SLA in that it uses what amounts to a photopolymer. It has a wide range of possible materials. It doesn't have a very big bed, but it gets fairly deep. This basically lets us print parts that are a plastic. It uses that photopolymer, and it also uses a support material which I kind of think of as close to snot. It's kind of a gooey, crumbly material, which you can see. It's on this one here, it just breaks off. And once you get done building the part, you have to go in the other room with a water jet and basically hose it down and take all that extra material off of it to get to the part. But it has relatively fine detail. These are all built as separate pieces and put together, but it gets down about 16 microns. The hard part is getting something that tiny clean. And again, it can print parts that work all as one piece. They're all printed as one time, hinges and all. And the top hasn't been cleaned, so I'm not going to get it. So this is the other technology, noisy as it is. Well, I'm running out of technologies to tell you about. The corner, this is a Chinese product called the UP. It's another fused deposition modeling type of 3D printer. It has a much smaller build area. And again, it's using ABS wire, melting it and extruding it where it wants the part to be. The low-end machines don't have a very high quality. I mean, you can look at these, they're not that great. But they're home hobbyist machines for people just starting out. That particular machine is about $1,500. There's some cheaper, there's some more expensive, but they all work pretty much the same way. They extrude ABS plastic. They're just now starting to come out with what they call home SLA machines that work on the principles of the photopolymer that we talked about in the other room. They're about $3,000 and they're pretty scarce right now. They haven't really hit the home market that well. They're just getting going, but they promise to have much finer detail than the ABS plastic FDM machines will. Any questions? Any ideas? Oh. No questions at all? Then I failed. I got to have something I didn't do right. Well, I'm running out of things to tell you about here. I was getting 40 minutes. That didn't take long. We also, right now, one of our guys is in Tucson, Arizona at what's called the AMUG, or Additive Manufacturers Users Group. It's people from all over the world that use 3D printing machines go to that meeting and they teach each other their little tricks, their little ideas and workshops to get the latest and greatest ideas across to everybody. And the world is constantly coming out with new machines and new ideas. The polyjet technology in the back, its big brother is the Connex, which is the digital material. Well, now they're coming out with one that actually prints in color. The bad news is you have to pick from a range of colors because you put in certain cartridges and it mixes them on the fly. But each set of cartridges can give you a certain range of like all the yellows or all the oranges or whatever. So you can technically print hard, durable plastic parts in color, which comes in handy. We got any Halo fans in here? No Halo fans? Objet, the maker of that machine, has actually printed a Master Chief about this high with all the different colors for his armor, his face, and everything, and it's all printed as one piece because they can digitally mix the colors on the fly as well as the hardness and everything else. So it's kind of, you're only limited by your imagination. There's a way to do anything. If you have any questions, I'm more than willing to try to answer them. If not, the big guy in the other room should know the answer.
Was What's the relative cost of all the machines?
They all over the place. Like I said, that one's about $1,500. That gives you an idea of a low end.
Bigger ones.
The machines in the other room that we saw, the force forges are right around $1,500. The Sony machine, they don't sell in the United States anymore, so I couldn't get you a current price. The SLS machines, those are used machines. In fact, one of those two machines was up at Pratt & Whitney when the Northridge earthquake hit and literally fell through the floor to the next floor. They went in the next day with a crane, picked it up, moved it off to the side, cleaned it up, hooked it up, and started printing. They're built like tanks. You know, the market changes on used machines, and most of those machines are very old used machines. As far as an SLS machine goes, $100,000 to $1.5 million, depending on how big and what you want it to do. Metals machines are around $1 million, but they print metal and they end up saving you a fortune. If you take a block of titanium, Ti6, that's what, about 70-some dollars a pound, give or take, depending on what Russia thinks to charge. But say $70 a pound for a block of titanium. Well, using his CNC process or some of the other processes, what are you doing? You're whittling away that block to get to the part you want. And what you now have a part and a whole pile of scrap, right? So where'd your money go? More of your money went to scrap than it went for the part. With the metals machine, you put the powder in the machine, the part comes out, all the leftover powder goes right back in the machine. So you only pay for what you use. So the end result is it's far more economical to use a metals machine than it is to use CNCing and all the other. Plus, you can design chambers like, you can have a turbine blade and actually build the cooling chambers all the way in it because you're printing it as you go. So it's real easy to leave out metal where you want the cooling chamber to be all the way up. You can build honeycomb, you can build whatever you need to make the part function the way you want it to. Unlike other, there's only 3 ways to do something. Besides additive, you have subtractive and you have formative, whether you stamp it out or you whittle it away. And each of those has limitations on what you can build for internal structure or shapes, etc., that you don't have with additive manufacturing. Basically, you can dream it, you can build it.
You said it takes like energy to you need to heat it up. Like there's a time for the metals machine that it has
Well,
to
the SLS machine has to ramp up slowly. It basically has to get, in our case, we're using nylon 11. We have to get that center pot to 183 degrees centigrade, which you have a heater underneath and heaters up above. So it's not a fast process. It takes time to heat it up. But you're literally heating the whole chamber. The feed bins are heated to 83 degrees centigrade, so the powder's already partially warmed up before it gets there. Then it has to heat to the right temperature, then the laser runs. And then again, now that it's done, that whole bed is 183 C, you've got to get it cooled back down. That's what takes the most time, 6, 7, 8 hours, to cool the bed back down to where you can go in there without it being inert and take the part out without damaging the material.
So it's not ideal for like batch manufacturing, right?
Well, we always say it's rapid, not instant. You know, it's much quicker than doing a lot of things other ways. If I had to cast all those parts, then I have to go through a process of ultrasonically welding them and everything else, which is a lot more production, a lot more people doing things, you know, quality control checks. Here, I'm just printing it as one piece, shaking it off, and it's ready to go. So it's much more efficient, even with the wait time. Yeah?
Talking about material properties versus CNC machining, is it similar in terms of strength or hardness?
Well, as far as metals go, they have found that the grain structure they get for, like, say, titanium in an SLS machine is better than they get with casting. It's actually more uniform. And we've done testing here with an Instron machine and some of the graduate students to where the orientation of the part doesn't seem to make a difference in the actual strength of the material. So I can lay it flat, I can lay it on end, I can lay it at a 45-degree angle. Doesn't matter, it still prints pretty much the same. You know, cosmetically, you learn over time which way to orient it to make it look the best. The side you want should be up, not down, because everything needs support. You know, in 3D printing, if I have an angle, think of liquid plastic. Is liquid plastic going to hang in the air? No, it's going to droop. So I have to provide support material underneath it to hold it up like a scaffolding all the way. So that's going to leave a little mark where the scaffolding touches the part. So I would orient the part so the faces I worry about aren't touched by the scaffolding. And there's software to do that.
Does it usually require like surface machining afterwards?
Not normally. You can finish parts. A lot of people paint parts. You know, there's plastic primers that'll grip into the plastic and prime it with a thin coat, and then you can paint on top of it. We did models for Hester Studios. They did maquettes for Shrek 1, 2, and 3, and a couple of other movies. And we've done printed models for them that they've gone out and painted. You couldn't tell that they didn't manufacture. I mean, they're gorgeous when they're done with them. They really look high quality. So you can finish 3D parts. The trick is knowing what finishing techniques to work for what material. It varies depending upon the machine and what material you're using. Like FDM, you're literally, it's like a little tube laid down, and then the next one's a little tube on top of it. Well, if you look at that, it goes in and then out. So you literally have a kind of a ribbed surface. But we found that you could take a rag with a tiny bit, damp, not wet, of acetone and basically wipe it across there, and it liquefies it just enough to fill it all in and smooth it out to where you have a smooth surface, and then you can go ahead and paint it. Or you can use a little bit of body filler to fill it in and then paint it to where nobody knows it was ever those little bumpy lines there. There's lots of finishing techniques. It's a whole world into itself, really. In fact, some of our past interns have gotten jobs out in shops out in town where they started out, that's what they were doing, finishing. Because they had the experience of doing it here. It worked out pretty well for them. But yeah, you can really finish some nice parts when you're doing, depending on how you do it. Any other questions? Oh, such a lively bunch. But yeah, 3D printing is, it's not the cure-all, the end-all, but it can save a lot of time and effort. It's just now starting to really get into the manufacturing side of it, especially SLS. That's being used by Boeing. It's being used by a lot of companies. I've seen companies that have printed entire wings for a RPV on an SLS machine. It's one piece. They take it out, shake out the powder, and the wing's ready to go. And it's lighter than it would be if they had to do it some other way, but structurally sound. So, like I say, you think it, you can do it.
How long would that take to build the whole, have the whole?
Depends on the side of the wing and the machine. We're talking very big machines, not these little ones. But it's going to vary depending on the material and the process, but hours, you know, no more than a day. But the end result is they have the part. And they're pretty well confident that the structure is the way they want it and everything is the way they need it. That's about all I have to give you, unless you have some more questions. They're all in a hurry to get out of here. Have a good day. And we're here. If you need, you know, you can always make an appointment with Ed or Ben. Ben is our other guy. He's the kind of director of research. Right now, he's the one that's down in Tucson at that conference. So he's going to teach hydrographic printing, where they literally take, oh, he stole all the parts. You literally take a part like this, which is basically a plastic part, and they literally have a technique to map a texture over the top of it. And that's how the hydrographic printing is how they do things like gun stocks with the nice little camo pattern, or dashboards with a walnut grill, you know, the whole 9 yards. Most of that stuff is hydrographic printing. It's basically a film of ink with a polyvinyl alcohol background. And then you set it on the water, and I mean set it, you don't put it in the water, it just lays on top. And the ink gets wet. And then you spray an activator on it that dissolves the polyvinyl alcohol. And then you take your part and dip down through it. And it's like a decal, it just sticks right to your part. So it's another way you can finish parts. There's lots of ways to finish parts. Okay, well, I do have one thing I can show you. Remember that powder-based machine? Well, you can print whatever you want on it. This was made in SolidWorks. I won't pass it around because last time they broke his arm in several places, but you can print whatever you want. If you can design it, you can build it, you can print it. This one's all solid, it's not hollow.
Was that made by a student?
No, it's made by me. I took a SolidWorks course years ago, and as a final project, I made Bender. So, he went through several evolutions. He was a little fat the first time, and I had to skinny him down some. Put him on Jenny Craig, and then he worked out well. But if you want, you know, and you've got text in here, it says booze, 100 proof, you know, so you can print fine details. Depends on the machine how many details you get. And that's part of the process of working with rapid prototyping, is learning the limitations of each machine. Each machine has pluses and minuses, things you want to use it for, things you don't even begin to use it for, things that you know better than to try. Like if you have lettering and you decide you want to cut it all the way through something, well, gee, what happens to the little center section of the letter D once you've extruded all the way through? It falls out. And suddenly you have a big D with no middle, or an R with missing part. So these are things that you learn through trial and error. You go in and play with the software, you play with the equipment, and print and see what happens. And it's an education process. You learn more from your mistakes than you do from your successes, unfortunately. Different materials. You see, we have a soft rubber skin. We have a hard skeleton, we have a plastic skeleton, we have a repair piece. If I can remember which way the repair piece goes.
What's the repair piece for?
Well, say 3D rapid prototyping is being used in medical devices extensively. We've had a couple stories where early on we had a Marine in Iraq, you know, the big metal Connex box, those long big containers. Well, the wind blew the door open and it hit him right across here. And it put a big dent in his forehead. And being a Marine, they stitched him up and he went back to duty. Well, a few weeks later, he lost his sight in this eye. And they couldn't figure out why. So they were flying him to San Diego from Iraq, and in the meantime, they sent us his CAT scan. And we had some software that let us take the CAT scan and rebuild it into a 3D model. We printed on the powder-based machine a skull, life size, his skull. And when you looked at it, you could see that a bone had grown inward and pressed on the optic nerve. But they couldn't see that in the CAT scan because the individual layers made it hard to see this is a big protuberance. So the end result was we sent the model down to San Diego. It got there before he did. They did the surgery based on that model, and he got his sight back. So it was a success. We've worked with UC Berkeley on maxillofacial reconstruction, where you get accident victims that get in an accident and the whole side of their face is crushed. It used to be that they would take those people into the operating room, open them up, and then while they're laying there, they'd be fitting titanium braces and everything to try to get things back to looking normal. That meant the person was laying in the operating room open 5 to 6 hours. Okay, we worked with them to develop a procedure where the SLA machine in there, the big machine, the resin in there can be sterilized. And when it's sterilized, it has a pinkish tone that tells you it's sterilized. So they would send us the CAT scans, and we would mirror the good side over to replace the bad side. We would then print a skull, life size, send it to them. They sterilized it. They would take it in the operating room before the patient, and they would bend all the braces on the skull to fit the patient. Then they would bring the patient in, open them up, install the braces, close them up, and they're out in about an hour. So their recovery time was much less, their success rate was much higher, and they got a more uniform product out of it. So there's a lot of medical ways that 3D rapid prototyping is working. In fact, they're working on printing organs, printing blood vessels. There's somebody trying to print a kidney right now, as far as I know. The big thing is, I like the idea of arteries, because right now, if you become a diabetic and you have to have a transplant of an artery, well, they got to take it from somewhere else. Okay, imagine if they can take your stem cells and grow an artery to put in there to where the rest of your body doesn't get attacked to fix that part. They have the same thing with bones. They print a scaffolding and then they seed it with stem cells. And they grow bone in the exact size and shape they need. And it's your bone because it's your stem cells, so your body doesn't reject it. So the medical device field for 3D printing, well, it's really not 3D printing, it's additive manufacturing is the official term. But additive manufacturing has a bright future in medical modeling, and it's growing by leaps and bounds. In fact, worldwide they think additive manufacturing is going to be a $3.7 billion business by 2017. I think that's an understatement, to be honest with you.